Okay, today I shall be speaking on supersymmetry. It is a modern theory of quantum fields in which bosons and fermions are treated on an equal footing. What are bosons and fermions? Bosons are have integer spin particles like the photon or the W boson, the gauge bosons which appear in propagation as propagators of the nuclear forces. They all have integral spin, and whenever they have integral spin, it is a well known fact in quantum theory that they satisfy the Bose-Einstein statistics for indistinguishable particles. Fermions satisfy the Fermi-Dirac statistics, and they are also indistinguishable particles, but they are characterized by the fact that they have half integer spin. So, today most of the theories in the earlier part of this century of the last century were either purely bosonic theories like Maxwell's equations for the photon or the Yang-Mills field equations for the gauge bosons, and they were all or Dirac's equation for the fermion, or for the gravity which is a spin 3/2 particle, again you have a wave equation. So, you have separate wave equations for the photon for the bosons and separate wave equations for the fermions, but there is no linking between the two. Is it possible to develop a theory in which bosons and fermions are put on the same footing, so that you can study the interactions between the two and you can see how one field affects the other. So, success came when people like Weinberg, Salam and Glashow, in fact Salam and Statidy, they proposed a supersymmetry theory in which you have bosonic generators P mu, namely the momentum, and the 4 angular momentum J mu nu. These are the bosonic these are the generators of the Poincare group. P mu's are the canonical, P mu's are the 4 momenta, that is P0 is energy and P1, P2, P3 are the momentum operators. J mu nu are the 4 angular momentum operators, namely you can write them as q x mu j x mu p nu minus x nu p mu. They satisfy the Lorentz algebra Lorentz algebra commutation relations. These are the generators of the Poincare transformations, namely space time translations, rotations in space and Lorentz boosts. So, you can write down the commutation relations between this, and on the other hand, in supersymmetry theory, apart from this you should have fermionic generators QA and maybe QA dagger. So, it is natural to expect that there is some sort of a, instead of defining commutation relations, we define super commutation relations, that is, if x is a fermionic variable and y is a bosonic variable, then rather than defining x, let us say x and y are two variables, you write the super commutator as xy minus 1 power px py yx, where px is the parity of x and py is the parity of y. If x is a bosonic operator, then px is 0, its parity is 0. If x is a fermionic operator, then its parity is 1. So, if x and y are two fermionic operators, then px and py become 1 and this becomes an anti-commutator. Likewise, if either x or y if x and y are bosonic operators, then px and py are 0 and it becomes a commutator. And if either x or if one of them is a bosonic operator, another is a fermionic operator, in that case again 0 into 1 becomes 0, so you get a commutator. So, just as you have Lie algebra of the Lorentz group in which you get the relations like J mu nu comma J rho sigma equals eta mu sigma J nu rho plus eta nu rho J mu sigma minus eta mu rho J nu sigma minus eta nu sigma J mu rho, and similarly P mu comma P nu is 0 equal to 0, and J mu nu comma P rho will be again a combination, linear combination of P mu's of P alphas. Okay, you can calculate that commutation relation very easily. So, this is a Lie algebra, that means it is closed under commutation relations. under, of course, it is a vector space is closed under linear combinations, and it is also closed under commutation relations. Likewise, a super Lie algebra should be closed under super commutation relations. So that you enlarge the number of symmetries. In supersymmetry we enlarge the number of symmetries, namely we require both symmetry, we require symmetry under space time translations and symmetries under boson fermion transformations, that is boson fermion exchanges. Okay, so if you take two fermionic generators QA comma QB dagger, and you, since both of them are fermionic, you should talk about an anti-commutator, because the parity of QA is 1 and the parity of QB is also 1. So the, if you take a product of two fermionic operators, it should be a bosonic operator. So you should have something like sigma mu A B P mu. Okay, so where sigma mu A B are some numerical constants, and P mu is the momentum operator, 4 momentum operator. That means the anti-commutator between two fermionic variables is a bosonic variable. Likewise, if you look at, there could also be, of course, internal symmetry generators. Internal symmetry generators. Likewise, if you take the commutator between a bosonic operator and a fermionic operator, so you will take now a commutator, because this has got parity 1, this has got parity 0, and this has got parity 1. So this should be a fermionic operator, and it turns out to be 0. It turns out to be 0. So you get an enlarged super algebra by including fermionic generators into the picture. Salam and Strategy, they proposed a representation of Salam and Strategy. They proposed a representation in terms of super vector fields. Representation of a super Lie algebra in terms of super vector fields. What is the representation? If you take two, let us say x's, say let us say you look at x comma y, the super commutation, this is xy minus 1 power px py yx. So if you take a representation, say pi x comma pi y, the super commutation relationship of this should be equal to pi x pi y. So this should again, you are looking at a representation of super operators of the super Lie algebra. So this should be again, it should be, if you call this as z, then this should be pi z. So the idea here is to represent, instead of looking at vector fields, operators acting on vector fields as you do in bosonic theory, like the wave operators, momentum operator, angular momentum operators, and so on, you look at super vector fields, that is functions of the bosonic coordinates and fermionic coordinates. Thetas are the Majorana fermionic parameters, and x are the bosonic variables, namely space time x mu and theta mu. So x is nothing but x mu and theta is nothing but theta a, where a goes from 1 to 4, or you can say it goes from 0 to 3, and mu also goes from 0 to 3. So these are the fermionic variables, and they anti-commute. That means theta a, theta b plus theta b, theta a is 0, whereas the bosonic variables commute with each other, x mu minus x nu is 0. So this is a super vector field. Obviously the product of more than 4 thetas is 0. So a super vector field can be written as a polynomial in thetas of degree 4. You can write this as, say, s0x plus skx theta k summation over k equals 0 to 3 plus, say, s1, let us say s0 plus s2 kl of x theta k theta l, k less than l less than 3 greater than 0 plus summation s3 klm of x theta k theta l theta m, 3 of them, and finally summation s4 k s4 of x into theta 0, theta 1, theta 2, theta 3. If you take a product of more than 4 thetas, they will be 0 due to the anti-commutation relations. So, such a field is called a super vector field. This is called a super vector field. It is called a super vector field, and the representations of the super Lie algebra are constructed as linear differential operators acting on such super vector fields, just as the momentum representation in canonical quantum mechanics is minus I dou by dou x mu, and it acts on a vector field. Likewise, the representation of angular momentum is so this is the generator of the space time translations. That means, if you take e power I k mu p mu, or if I pay xi mu p mu, this is nothing but e power xi mu dou mu acting on phi x, which is equal to phi of x plus xi, a translation. Likewise, if you look at angular momentum, it is e power I omega mu nu j mu nu, and acting on phi x, it will give you a Lorentz transformation corresponding to this acting on this. That means, it will be phi of lambda of omega acting on x, inverse acting on x. So, j mu nu's are the four angular momentum operators, where lambda omega is the Lorentz transformation corresponding to the infinitesimal anti-symmetric matrix omega mu nu. That means, lambda omega can be written as e power I omega mu nu into okay, it is so it is simply the anti-symmetric matrix. It is an anti-symmetric matrix corresponding having entries as omega mu nu. So, e power I omega, lambda omega is simply e power I omega. It is a finite Lorentz transformation generated from infinitesimal Lorentz transformations. Omega mu nu's are anti-symmetric matrices. Why they are anti-symmetric? Because if you raise this and look at, say, omega mu, suppose I call this as x mu tilde, then you can verify that the anti-symmetry where omega nu mu is obtained by raising it, u rho omega mu rho, by raising this index. Then you can see that if you look at this plus x nu, so this is an infinitesimal transformation. So, if you assume this is an infinitesimal Lorentz transformation, so you can show that up to order omega, if you neglect order omega square, then x mu tilde is equal to x mu, which means that the Lorentz plus order omega square, which you can neglect. That means, this is an infinitesimal Lorentz transformation. This holds good provided omega mu nu is anti-symmetric. Okay, omega mu nu is anti-symmetric. So, this is a representation of the Lorentz group on the space of fields. Likewise, you should generate, and of course, if you take the infinitesimal form of this, then you get a representation of the Lie algebra of the Lorentz group acting on vector fields or acting on scalar fields. Okay. So, likewise, in the case of super vector, if you take a super vector field, you want to find a linear operator. You want to find a linear operator which will represent supersymmetry transformations, namely it will represent the supersymmetry algebra. So, Salam and Strategy, they have proposed gamma 5 epsilon dou by dou theta plus gamma mu theta dou by dou x mu. Suppose you call this as, say, q, suppose you call this as q. That means, theta is a vector of Majorana fermionic variables, theta 0, theta 1, theta 2, theta 3. Gamma mu are the standard Dirac matrices, and gamma 5 is gamma 0, gamma 1, gamma 2, gamma 3, and epsilon is nothing but I sigma 2, 0, 0, I sigma 2, which is an anti-symmetric matrix. I sigma 2 is 0, 1, minus 1, 0, and 0, 1, minus 1, 0. So, this becomes a super vector field, and you can use the anti-commutation, just as you have commutation relations for bosonic variables, canonical commutation relations dou by dou x nu. This commutator is nothing but minus of delta mu nu. Likewise, you could define in the case of fermionic variables theta a comma dou by dou theta b. This anti-commutator is nothing but delta a b, right. So, if you use this commutation relations and use the fact that bosonic variables commute with the fermionic variables, then you get a representation of the super algebra, Lie algebra. So, this is a vector. So, this is nothing but QA has got components A going from 0 to 3. So, you can see easily that QA comma QB is equal to this anti-commutator. This will be nothing but gamma mu dou by dou x mu into some constant. You can check that very easily. It is of course a linear combination of dou by dou theta plus gamma mu theta dou by dou x mu. Suppose you take the ath component and the bth component, then gamma 5 a, let us say AC dou by dou theta c, this is the ath component, plus gamma mu a c theta b theta c dou by dou x mu. Suppose you take the anti-commutator of this quantity with gamma 5 bc or bd dou by dou theta d plus gamma mu bd theta d dou by dou x mu. Suppose you take the anti-commutator, what will happen? Dou by dou theta c, the anti-commutator between dou by dou theta c and dou by dou theta d is 0, right, because there are two fermionic generators. So, the anti-commutator, and since the theta's anti-commute, correspondingly dou by dou theta should anti-commute, that means this must be 0. Likewise, the commutator between two bosonic variables, so dou by dou x mu comma dou by dou x nu is 0. But what will happen is, if you take the anti-commutator between dou by dou theta c and theta d, there you will get a delta c d. So, this will give you a term gamma 5 AC, the anti-commutator between dou by dou theta c and theta d, that will give you theta d, that will give you delta theta delta d c. So, if you look at gamma 5 AC, here you will get gamma mu bd and then delta cd and then dou by dou x mu. So, dou by dou x mu. Likewise, if you look at the anti-commutator between this term, this is linear in theta c and linear in the moment in the bosonic momentum with theta d, that will give you again a term of proportional to dou by dou x mu. And if you look at the commutator, the anti-commutator between dou by dou theta d and theta d, if you look at the anti-commutator between theta c and theta d, that will give you 0. So, the last term also will not contribute to this anti-commutator, theta c comma theta d anti-commutator is 0. So, in effect you will get the whole thing, this whole commutator is proportional to dou by dou x mu, and you can check explicitly that this anti-commutator qa comma qb can be written as gamma mu ab into dou by dou x mu. So, you get a representation of the supersymmetry algebra, of the supersymmetry Lie algebra in terms of vector fields, super vector fields acting on super fields. Now, you want to know, you want to develop a theory in which the different bosonic fields like the Maxwell field, the non-abelian gauge fields appearing in nuclear forces, namely the W and Z boson field, and then the fermionic fields like the Dirac field, the Gaugino field and other fields, they all appear as components of a big super vector field, and you want to define from this super vector field, you want to construct a Lagrangian which is a function of all the component fields in such a way that this Lagrangian is invariant under supersymmetry transformations, namely under the infinitesimal transformations defined by these super symmetry operators. So, your QA defines the supersymmetry operator, infinitesimal supersymmetry transformation operator, but you have it as a anti-commutation relation here. To get a commutation relation, you must put a Majorana fermion which I call as alpha A. Alpha A is a Majorana fermion parameter, so that this becomes alpha transpose Q, or alpha transpose, you can say alpha A, you can say alpha transpose epsilon Q, which is also written as alpha bar Q, or alpha transpose gamma 5 epsilon Q. So, gamma 5 epsilon is an anti-symmetric matrix. So, if you multiply this by a Majorana fermionic parameter, these anti-commutation relations will become commutation relations between these quantities. And so you can define a infinitesimal supersymmetry transformation as a commutator with these generators, right. So if you take any vector field S, super vector field S Sx theta, and suppose I form the commutator with the super vector fields after taking into account the infinitesimal Majorana Fermion parameter, then that will give you a change in the super vector field. Just as when you look at, for example, a momentum operator, if you take the momentum operator, you dot product with a bosonic parameter and you take the commutator of this with a vector field phi x, what is this equal to? This is equal to xi mu into minus into I dou by dou x mu with phi x. This commutator is nothing but if you put, let us say I put I here, so that this will become minus, and so this will become minus of xi mu dou by dou x mu, or xi mu dou by dou x mu, xi mu dou by dou x mu acting on phi x, which is an infinitesimal translation. So if you translate phi x to phi x minus xi, then this becomes phi x minus xi mu dou phi by dou x mu. So you are able to generate an infinitesimal translation by taking commutator with a bosonic generator. Likewise, if I take a commutator with the angular momentum generator, let us say I take an anti-symmetric matrix xi mu nu and put j mu nu here and take the anti-commutator with the take the commutator with this, then this will be equal to what? It will be equal to an infinitesimal Lorentz transformation acting on phi x, right, corresponding to the parameters xi mu nu, anti-symmetric matrix xi mu nu. So this will give you nothing but phi x plus phi of you can say it is nothing but no, it will give you nothing but phi x minus xi mu nu x nu. So phi of x mu minus xi mu nu x nu. So where xi mu nu is an infinitesimal parameter, that means this is an infinitesimal Lorentz transformation which would include rotations and boosts and so on, because if you expand this will give you phi x minus xi mu nu x nu dou by dou x mu, xi mu nu x mu dou by dou x mu phi of x. So this is nothing but p. So you get that since xi mu nu is an anti-symmetric matrix, this could also be written as xi mu nu by 2 times x nu dou by dou x mu minus x mu dou by dou x nu, which is precisely the angular momentum generator. That means if you take the commutator of a scalar field with a bosonic generator like 4 angular momentum or momentum, then it will be equal to and it is equal to making a transformation of the scalar field by an infinitesimal Lorentz transformation. Likewise, if you want an infinitesimal supersymmetry transformation, you must take the commutator with a supersymmetry generator, namely the super vector field of Salaman-Strategy, and that represents the super vector fields. They represent, as we saw, the supersymmetry algebra, namely commutators between fermionic generators should be bosonic generators, commutators between two bosonic generators should be a bosonic generator, and the commutator between a bosonic and a fermionic generator should be a fermionic generator, which can be 0, and you can also have central charges, namely the commutators can include internal symmetry operators. So let us now see how to construct Lagrangians which are invariant under such supersymmetry transformations. If you are able to construct that, then it means that you have a coherent theory of bosons and fermions treated on the same footing. So the idea is, first, instead of writing a super vector field in this way, what we will do is we will write a super vector field as, say, a scalar field which I call Cx. These are all bosonic fields, the components are all bosonic fields, plus Cx plus, say, I say theta transpose epsilon into psi x or omega x. There are 4 of them. Epsilon is an anti-symmetric matrix. So theta transpose epsilon omega x is a 4 component spinor. So this gives you all the linear terms. because this is equivalent to making a combination theta A into Fa, theta A Fa summation A equals 0 to 3. So this includes this is the first, this is linear in theta, then linear in, then quadratic in theta terms will be of what form? Theta transpose epsilon theta times mx plus theta transpose gamma phi epsilon theta into nx plus, I will just explain this, plus theta transpose epsilon gamma mu theta into v mu x summed over mu equal to 1 to 3, 0 to 3, plus you will have theta transpose epsilon theta into theta transpose gamma phi lambda x. So this will be a fermionic term, you can say, you can add to this plus some A times omega x or omega times A times omega x, okay. Theta transpose gamma phi epsilon, theta transpose epsilon theta, theta transpose gamma phi, theta transpose gamma phi epsilon lambda x plus A times dou omega x. Let me write it clearly. The cubic term is theta transpose epsilon theta into theta transpose gamma phi epsilon lambda x plus A times dou omega x, okay. That is the cubic term, and obviously 4C3, that should be 4 components, and there are obviously 4 components here, because although this is a scalar, this is simply a scalar bosonic variable. When you multiply two fermionic variables, major order fermionic variables, you get a bosonic variable, and this is theta transpose this. So there are 4 of them here. There are, lambda is a 4 component spinor, omega is also a 4 component spinor. So there are 4 components here, namely you can write this as a linear combination of theta 0, theta 1, theta 2, theta 3 with coefficients being the different components of gamma phi epsilon lambda, plus you have a 4th component theta transpose epsilon theta and then whole square, that is quadratic in theta, 4th degree in theta into dx plus b times the D'Alembert acting on Cx. So you see all the, you can write a super field in this way with different components written in a way so that you can identify. You should remember that if you look at the order 2 term, what are the possible independent anti-symmetric matrices? Gamma phi epsilon, epsilon gamma mu. There are 4 here, epsilon gamma, these are all anti-symmetric matrices, that is the transposes are negative. So there are here 4 of them, here there is 1 of them, here there is 1. So 4 plus 1, 5 plus 1, 6, that completes the total set of 4 cross 4 anti-symmetric matrices, right. If you look at how many anti-symmetric matrices, what is the dimension of the vector space of anti-symmetric matrices of dimension of size 4 cross 4? Here you have 1, here you have 1, 1, here you have 1, 1, 1, all the diagonals should be 0. So if you specify the entries above the diagonal, then there are 1, 2, 3, 4, 5, 6. The corresponding below the diagonal will also be negatives of this. So there are in all only 6 linearly independent anti-symmetric matrices of size 4 cross 4, and they are covered by epsilon, gamma phi epsilon, epsilon gamma mu. Epsilon transpose is of course minus epsilon. Gamma phi is what? Gamma phi is I2 0 0 minus I2. So gamma phi epsilon becomes epsilon 0 0 minus epsilon. Epsilon is nothing but I sigma 2. Gamma phi epsilon is nothing but gamma phi, it becomes I sigma 2. Let me write it this way. Gamma phi epsilon is nothing but I sigma 2 0 0 minus I sigma 2, and epsilon is I sigma 2. Epsilon is nothing but I sigma 2 0 0 minus I sigma 2. Since sigma 2 is an anti-symmetric matrix, the Pauli matrix sigma 2 is 0 minus I 0. So you get an anti-symmetric matrix here. So that covers all the 6 anti-symmetric matrices. The 4th degree terms in theta are only 1. So there is only one linearly independent combination. If you look at any term like theta theta transpose, since the theta a's anti-commute with each other, namely theta a theta b is equal to minus theta b theta a. So, this should form an anti-symmetric matrix. So, this can be written as a linear combination of the 6 anti-symmetric matrices which I just told you. Namely, you can write it as f1 theta into epsilon plus f2 theta into gamma 5 epsilon plus f3 mu theta into epsilon gamma mu summed over mu, and you can get f1 theta, f2 theta, f2 mu theta by multiplying both sides by epsilon and taking the trace. So, you can write effectively f1 theta as something proportional to theta transpose epsilon theta. Similarly, you get f2 theta by multiplying by gamma 5 epsilon and taking the trace and using the orthogonality of epsilon with gamma 5 epsilon gamma 5 epsilon, or gamma 5 epsilon with epsilon gamma mu, or epsilon with epsilon gamma mu. If you use that orthogonality, then this will be this, and f2 theta will be nothing but theta transpose gamma 5 epsilon theta, and f3 mu theta will be nothing but theta transpose epsilon gamma mu theta. So, you get, if M is an anti-symmetric matrix, say if you take theta transpose m theta, okay, if it, now this is a scalar, if M is any matrix, then you would expect that this is equal to its transpose because it is a scalar. So, you would be tempted to write this as theta transpose m transpose theta, but this is incorrect. You should put a minus sign, because when you interchange the two thetas, a sign change occurs due to anti-commutativity. In particular, if M is an anti-symmetric matrix, then theta transpose m theta, okay, it will give you, this is the same as theta transpose m theta, right. So, it will tally if M is an anti-symmetric matrix. If M is a symmetric matrix, then this becomes 0. It means if M is a symmetric matrix, then theta transpose m theta becomes 0 in that case, if M transpose is M. Okay, now let us see how to define supersymmetry transformations. If you look at, say, Cx, write down all the terms, theta transpose epsilon omega x plus theta transpose epsilon theta into mx, these are bosonic fields, plus theta transpose gamma 5 epsilon theta into nx plus theta transpose epsilon gamma mu theta into v mu x plus theta transpose epsilon theta into theta transpose gamma 5 epsilon into lambda x plus a times dou omega x. When you say dou, I mean gamma mu dou mu, plus of course a fourth order term theta transpose epsilon theta square into dx plus b times the D'Alembert acting on Cx. So, if you want to look at an infinitesimal supersymmetry transformation to this, then I apply the operators Qa. So, alpha transpose q, alpha transpose epsilon, or alpha bar q acting on Sx theta, that will give you an infinitesimal supersymmetry transformation, because it is the commutator between alpha bar q and Sx theta. Just as you take, when you take the commutator between a generator of a symmetry and a field, you get the infinitesimal symmetry transformation acting on the field. So, this will give you an infinitesimal supersymmetry transformation where Q is the Salam-Strategy vector super vector field defined earlier. In particular, if you apply to Cx, what will you get? Q is what? Q is nothing but gamma 5 epsilon dou by dou theta plus gamma mu theta dou mu, dou by dou x mu. So, if you apply this, you will get a gamma 5 epsilon dou by dou theta of this, which is 0 because Cx does not contain 0. You will get then the second term will give you gamma mu theta dou mu Cx, which is first order in theta, right. So, that will contribute to this second term, namely theta transpose epsilon omega x. That means the change in omega x, is proportional to gamma mu dou mu x. So, it is proportional to dou mu, it can be expressed as a linear combination of dou mu Cx, right. The change in omega x is proportional to dou mu Cx, because you are equating the first degree term. You see, if you look at gamma mu theta dou by dou x mu acting on Cx, that will give you a linear term in theta. So, that will contribute to a change in the linear term here, whereas if you apply the same q to the second degree term, you will get a dou by dou theta acting on this, which will again give you a first degree term, right. So, that will also contribute to the change in omega x, whereas if you apply dou by dou x mu theta, gamma mu theta dou by dou x mu to the second degree term, you will get a third degree term in theta that will contribute to the change in lambda. So, and if you apply the super vector field to the third degree term, so dou by dou theta of the third degree will give you a second degree term in theta, right. So, that will contribute to the change in the second degree term. If you apply a gamma mu theta dou by dou x mu to the third degree term, it will give you a fourth degree term in theta, so that will contribute to a change in dx. So, in particular what will happen is that if you see the change in dx, the fourth degree term, it will come from the application of this component of the super vector field to the third degree term, right, and it contains a dou by dou x mu at complete derivative. So, you can see clearly that the change in dx is proportional to dou by dou x mu acting on this whole thing on lambda x. So, it will be dou by dou x mu acting on some function of x, a linear combination with constant coefficients. That means what I can say is that the change in the d term of the super vector field is proportional to, is a linear combination of dou by dou x mu acting on third degree terms f mu x. That means it is the total divergence. That means if you take a super vector field x theta and you take its d component, namely the fourth degree component minus the first one, and you consider d4x integral, this quantity will be invariant under local supersymmetry transformations, because the change in the d component, as we just saw, is a total derivative. It comes from applying the super vector field to the third degree component. So, you can construct a supersymmetric action using this idea by taking a super vector field and taking the d component. So, likewise, there is something called chiral fields. What is a chiral field? A chiral field, you can have left chiral fields and right chiral fields. So, left chiral fields and right chiral fields are super vector fields, are special types of super vector fields which are invariant under supersymmetry transformations, and they contain fewer number of terms, and they represent the matter super fields in the theory. So, you can have of course chiral fields and gauge super fields both. Gauge super fields generalize gauge fields like the Maxwell field, non-abelian gauge fields, taking into account their fermionic partners, super partners of the bosonic parts, and likewise chiral fields generalize the matter fields like the Klein-Gordon scalar field, the Dirac field, taking into account their super partners. So, like the Dirac field and the auxiliary fields. So, a chiral field contains only a component. A chiral field contains only the components. Okay, let us look at it this way. Suppose I take phi x. Suppose I define, given the fermionic parameter theta, I define 1 plus gamma phi by 2 theta, right. What is 1 plus gamma phi by 2? It is I 0 0 0. What is 1 minus gamma phi by 2? This is 0 0 0 I. So, 1 plus gamma phi by 2 theta will consist of the first two, theta L 0, the first two components of theta, and then 0 it will be there. Likewise, 1 minus gamma phi by 2 acting on theta, that will comprise of 0 and theta r. Okay. So, I call this as theta L and theta r, and then I define by making an infinitesimal supersymmetry transformation, I can make the gauge parts, namely I can make the gauge parts which come here as V mu, I can make it 0, I can make V mu 0, I can keep that conditionally preserved under the local supersymmetry transformation. So, this will be simply of the form a scalar field which is a function of x plus, I will just define this, x plus mu is x mu plus theta r transpose epsilon gamma mu theta L, maybe a factor of half, like this. So, of course, these are the theta L's and theta R's anti-commute. So, the transpose of this becomes theta L transpose epsilon gamma mu theta R, because epsilon gamma mu is an anti-symmetric matrix, plus theta L transpose epsilon psi L of x plus theta L transpose epsilon theta L into f of x plus, which can also be written as fx, because theta L transpose any two, if you have more than one theta L acting, if you have a cubic combination of theta L, it is 0. If you have a cubic combination of theta r, it is 0, because theta l comprises only of 2 of the thetas. So, anything say theta l cube, let us say theta l tensor theta l, this is 0. Likewise for theta r, but you can have non-zero values of theta l tensor theta r, because theta l's anti-commute and there are only 2 components of them, and theta r's anti-commute and again there are only 2 components of them. Okay. So, you can write a general left chiral field as a function of x plus and theta l. It satisfies a characteristic property that if you look at it is invariant, this superfield is invariant under supersymmetry transformation. That means, if I apply an infinitesimal supersymmetry transformation defined by the super vector field, then it will again be of the same form, right. And the additional advantage is that you of course, you can bring any, you can choose a gauge in which you can choose a gauge in which all this happens. That means, you expect that there are quadratic terms here. So, you expect that okay, I will just come to it. So, if you look at a left chiral field, so you can write it as phi of x plus theta l transpose epsilon psi l of x plus theta l transpose epsilon theta l into f of x plus, which is f of x itself. So, I can also write this as, if I substitute for x plus mu is equal to x mu plus theta r transpose epsilon gamma mu theta l. So, if I substitute this, it becomes phi of x plus phi dash of x, that means dou mu phi x into theta r transpose epsilon gamma mu theta l plus dou nu phi x into a product of 2 of them, theta r transpose epsilon gamma mu theta l into theta r transpose epsilon gamma nu theta l. This will be a quadratic there is only one term, one linearly independent term which is of 4th degree in theta, namely the product of all of them. So, you can write this as theta transpose epsilon theta into eta mu nu multiplied by this. So, this 4th term will become simply the wave operator, namely eta mu nu dou nu acting on phi x multiplied by theta transpose epsilon theta square, which is nothing but the wave operator acting on phi x into theta transpose epsilon theta square. So, you can simplify this. So, likewise, if you look at psi l of x plus, you can write it as psi l of x plus theta r transpose epsilon gamma mu theta l into dou mu of psi l x multiplied by theta l transpose. So, theta l transpose epsilon, you cannot go beyond that, because already there are 2 theta l's coming here. The next term will contain cubic term, the next term will contain 2 theta l's which will multiplied by the 3rd theta l will give you 0. So, you can have only so much. So, if you what exactly is a chiral field, how is it characterized by? It is characterized by the fact that you have got a scalar Klein-Gordon field here, a psi l which is a Dirac field here, and phi and psi are super partners of each other, that is phi is a bosonic field, psi l is a fermionic field, and if you apply a supersymmetry transformation to this, the change in psi l will come in terms of phi and also in terms of f. Okay. So, so that is the whole picture. Now, if you want to write down the, you can write, if you consider f of phi, where f is any function, and look at the f part means the coefficient of theta l transpose epsilon theta l. This is a chiral field again, it is a left chiral field. So, if you look at this quantity, what will it be? It will also be, if you take the integral of this, or if you look at the change in this under a supersymmetry transformation, this will also be a total derivative, you can see that, because if you take any a function of a left chiral field is again a left chiral field, because it is again a function of x mu plus and theta r transpose epsilon gamma mu theta l. So, if you look at phi f, this will change by a total derivative under a supersymmetry transformation. You can see that, because if you apply say gamma 5 epsilon dou by dou theta plus gamma mu theta dou by dou x mu, if you apply this to phi, if you apply this to phi x, then what will you get? what will you get? What will be the f term of this? That means the quadratic term in theta L. The quadratic term in theta L can come from either you take the quadratic term in phi and you differentiate with respect to theta, that will give you a linear term, that will not give you a quadratic term, or you take the linear term in phi and you multiply it by this, then you will get a quadratic term. What is the linear term in phi? It is nothing but theta L transpose epsilon psi L of x plus. Okay. But you are expanding this, so it comes out to be this. You are taking the linear term and multiplying it by this. So this dou by dou, other things are constant. So dou by dou x mu of this will come here into the picture, and here you will have gamma mu theta into this. So you can manipulate it to bring it entirely in terms of theta L, because theta L is 1 plus gamma phi by 2 into theta. So it is equivalent to if you look at a term like theta, if you write theta as theta L plus theta r into theta L transpose, theta r into theta L transpose will not give you, it is an anti-commutator, it will not give you anything. See, if you look at say theta into, if you look at theta r into theta L transpose, what will you get? The two, all the thetas anti-commute with each other. So you can write it as theta r, theta L transpose epsilon theta r into epsilon, because they anti-commute, and you can have other terms also, gamma 5 epsilon and so on. But since theta L and theta r are occupying different sectors, namely theta r occupies the first two entries and theta r occupies the next two entries, so that will not contribute. So you will get a term of the form theta L transpose theta epsilon theta L into a derivative, and this derivative is not going to contribute to the action, because the integral of a derivative becomes 0, a total differential becomes 0. But you can look at other terms coming. So the quadratic term is gone here, the linear term from here goes away. If you look at phi x, what is phi of x plus? Phi of x plus is phi of x plus theta r transpose epsilon gamma mu theta L into dou mu phi of x. That gives you a quadratic term in theta. Multiplied by theta you get a cubic term, that is not an f term. But if you take a dou by dou theta of this, then that will give you an f term, because dou by dou theta will remove one theta here, it will give you a linear term in theta r. Dou by dou theta, it will give you a linear term in theta r, but not a quadratic term. So that is also not going to contribute to f. But if you look at the cubic term in psi, you have say theta L transpose epsilon psi L of x plus, the cubic term is dou mu of psi of x into theta r transpose epsilon gamma mu theta L, that gives you a cubic term. If you take the derivative with respect to dou by dou theta, that will give you a quadratic term, and it comes with a derivative of psi, namely dou mu of psi x times a quadratic term in theta L, and since it comes with a derivative, its integral is 0. So the f term of a chiral field, left chiral field, is supersymmetric. Okay. So if you take any function of phi and you look at its f term, that becomes supersymmetric. To that I can add any function of, I can take a left chiral field and take its conjugate and look at the d component of this, because the d component of any supersymmetric, the d component of any superfield is supersymmetric. So this whole action is an invariant. This whole action is an invariant, and this is the Lagrangian this is the typical supersymmetric Lagrangian. Now what happens is that you want to know some more things. You want to know how does this Lagrangian differ from the usual Lagrangians obtained by considering the Maxwell Lagrangian, the Dirac Lagrangian interacting with the Maxwell Lagrangian, of course the Einstein Hilbert Einstein Lagrangian for the gravitational field, and the gauge boson Yang-Mills Lagrangian. How does this differ, and what extra interaction terms does this give to us? So if you take, for example, f of phi, if you look at f of phi, where phi is a left chiral field, of course you can define its complex conjugate by using the fact that theta L star is theta r star is theta L, where these are conjugates in the sense of as Majorana fermions, and if you look at psi L is a left handed fermion, so psi L star is a right handed fermion, psi r. So by a left handed fermion I mean that it is equivalent to multiplying it by 1 plus, if you use this projection operator on the space of left handed fermions, then these two are the same. So, this acting on psi is psi L, and likewise 1 minus gamma phi by 2 psi is psi r, where 1 plus gamma phi by 2 projects on the plus 1 eigenvalue of plus 1 eigenspace, plus 1 eigenspace of gamma phi, and 1 minus gamma phi by 2 projects onto the minus 1 eigenvalue eigenspace. If you look at this is nothing but if you look at the f component of this, I want to compute the f component of this, what do I get then? I get phi of x plus, which is phi of x plus dou mu phi x multiplied by theta r transpose epsilon theta L epsilon gamma mu theta L, plus another term which I just saw was the Laplacian acting on the wave operator, the L'Alembert wave operator acting on phi x into theta transpose epsilon theta square, okay, plus similarly other terms. So, if I expand this, I can expand it and up to 4th degrees in the thetas, because beyond that all the terms will become 0. So, you will get what? You will get f of phi x, which is not going to contribute. What is the f term here? The f term will come from here, right, from a quadratic term here, theta r transpose epsilon gamma mu theta L into this. So, you will get f dash of phi x multiplied by dou mu phi multiplied by a second degree term in theta, okay. A second degree term in theta is nothing but the second degree term in theta f dash of phi x plus, so it will be theta r transpose epsilon gamma mu theta L. So, this is the second degree term in theta, and you have a 4th degree term in theta also coming here. So, the second degree term will come from here, and just one second. If you take the f term in this phi of x plus, so theta r transpose epsilon gamma mu theta L, and you are taking the f term, you see you are taking f of phi x. So, this is nothing but f of phi x plus theta L transpose epsilon psi L of x plus theta L transpose epsilon theta L into f of x. This is again a function of x plus and theta x plus and theta L. So, it is a left chiral feed. Of course, if you expand this and I want to calculate the f component of this. So, the f component to get the Lagrangian, f is called the superpotential. So, if you expand this, you will get f of phi x, that will be the first term. What are the second degree terms in theta which come here? So, you can get an f dash of phi multiplied by you will get a term from here theta L transpose epsilon, then when you expand your psi L, psi L of x plus, you will get just one second. So, I want to compute this matter Lagrangian, and I want to show that it will give you the Klein-Gordon Lagrangian. If you take the dynamic term into account, it will give you a superpotential term. It will give you theta L transpose epsilon psi x plus. This does not give you the f term at all here, but you get an f term from here, right. So, you will get an f dash of phi multiplied by theta L transpose epsilon theta L into f x. This is the only f term that will survive here, right. You will not get anything from here, because if you expand phi x plus, you get phi x plus dou mu phi x into theta r transpose epsilon gamma mu theta L. So, you will get a combination of these of such terms theta r and theta l, which is not of the form theta l and theta, it is not theta l transpose epsilon theta l. So, that will not contribute. This also cannot contribute, because you will get, it cannot, this will not give you a quadratic term in theta l's, the only quadratic term will come from here. So, you will get this term here. Right. So, if you look at f of phi, f, this will be equal to essentially f dash of phi x, f dash of phi x multiplied by f. If there are many such fields, then it will be fn, summation over n, and you are going to take the real part of f of phi f. That means f of phi f plus f of phi star f by 2. So, that will be equal to summation f dash of phi n into fn plus f dash of phi n star a bar of this into fn star. Right. Now, you want to see how you want to make an analogy with the Dirac equation or with the Maxwell equation and so on. So, you consider the quadratic part, say phi star phi, this is the kinetic part of the Lagrangian. You are looking at the d part of this. So, you are taking k as phi star phi, a bilinear combination. More generally, I can take phi n, Cn and summed over all the n, but for simplicity let us just take one right chiral field and one left chiral field, and let us look at the d part of this. The d part of this will be what? The coefficient of theta power 4, the coefficient that is of degree theta of degree 4 in theta in this. So, phi can be written as phi of x plus phi star of x plus. So, it will become phi star of if you expand phi of x, what do you get? You get phi of x plus dou mu phi x multiplied by theta r transpose epsilon gamma mu theta l plus delta phi x acting on theta l transpose epsilon theta square. So, the d term comes out here, right. So, one of the d terms in this expression will come out if you take a product of phi x here. Let us say phi x is a real field, you take a phi x here, and in the second you make the expansion to get this. So, it will be of the form phi delta phi x, that will be the coefficient of theta transpose epsilon theta. So, that is one term which can come. I am taking it to be a real field, the real area, the scalar field to be real. So, you will get this term. The other term can come when you look at the Dirac component, namely theta l transpose epsilon psi l x plus. This will contain a degree 1 term, it will contain a degree 3 term, and you can get a coupling between the degree 1 term and the degree 3 term. Is it possible to get a coupling? What is the kinetic term? If you look at this quantity, this will contain theta l transpose epsilon dou mu of psi l of x into theta r transpose epsilon gamma mu theta l. So, this is a degree 3 term in theta l's, and this will club with the degree 1 term coming from psi l itself, right. So, the first portion of phi star will give you theta l transpose epsilon psi l of x. I took at this component in phi star, take the star, you get theta r transpose this r multiplied with the second component. I choose this term after making an expansion around, after substituting for x plus and making an expansion. So, this multiplied by theta l transpose epsilon dou mu psi l x multiplied by theta r transpose epsilon gamma mu theta, that is a cubic term here and a first degree term here. That means, I substitute for phi star, phi and phi star, their expansions. From phi star, from the first term I pick out only the linear term in theta l, which comes from psi l, the Dirac part without making the expansion. Here I may choose the Dirac part with an expansion. So, it becomes a coupling between psi r and dou mu psi l. That means, I get a term as psi r transpose dou mu psi l with some of course matrices in the middle of course. So, you get this sort of a term, that is the kinetic part of the Dirac Lagrangian. So, you will get plus psi r transpose some matrix, you will get dou mu psi l. You can work out the details of those matrices. So, into of course gamma mu will be there, right. So, let me write it down clearly. It will be psi r transpose gamma mu dou mu psi L, this sort of a thing will be there, and then you look at the superpotential part. So, you are adding to this the superpotential part, namely f of phi f, and just now I saw that in that f of phi f you will get a term like what do you get in what do you get here. So, you can write it as phi into delta phi plus psi r transpose gamma mu dou mu psi L plus you have f of phi f. What do you get here? You get the f by looking at, I just saw that this gives plus f dash of phi into f, that is the f term here, and anywhere anything else you get here. So, if you take the variation with respect to phi, you get the Klein-Gordon equation, the wave equation for phi without the mass term, but here you are getting something curious which is f. So, I want to just check this. If you look at say f of phi f, f of phi f, you can get only this, right. So, you get the Dirac equation dou mu psi L without any mass equal to 0, you do not get mass here. For the Klein-Gordon field, if you take okay, if you look at the gauge part, this gives you only the matter field Lagrangian, it does not give you anything more than that, right. It does not give you anything more than that. Can you get okay. Now, suppose you look at the gauge part is constructed by looking at gauge superfield interacting with the matter superfield. So, let us just write this down. So, the matter part is simply phi delta phi plus psi r transpose gamma mu dou mu psi L plus f dash of phi times f. The gauge part is you take a gauge superfield V of x theta, okay, and put it in the Wess-Zumino gauge, that means you apply a gauge transformation. So, what you do is you apply say e power V x theta and you apply a gauge transformation. Say let us say you have several components in a using Yang-Mills generators, symmetric generators T dot V, and suppose you take a gauge transformation, namely e power I omega x theta e power minus I omega star x theta, where omega x theta is an arbitrary chiral, is an arbitrary superfield, not necessarily it is an arbitrary chiral superfield, left chiral superfield. So, this will give you a transformation. Now, you can apply this transformation to bring VA into this Wess-Zumino gauge, that means you cancel out all the matter parts in VA to bring it to a Wess-Zumino gauge, means you look at e power T dot V x theta goes to e power I omega into e power T dot V x theta into e power minus I omega star, where omega is an arbitrary left chiral, superfield. So, it is a function of x plus, omega is a function of x plus and theta. So, by making this gauge transformation you can put V into a Wess-Zumino gauge in which it has got only gauge components, namely it has the only non-zero components are lambda, V mu and D, say dA. It contains only these terms, and then if you apply instead of applying a generalized gauge transformation, if you apply an ordinary gauge transformation, namely any lambda which is a function of only x plus, then it will remain invariant, you can prove this. So, if you look at for example something like I define the super derivative d to be equal to gamma 5 epsilon dou by dou theta plus gamma mu theta dou by dou x mu minus, I put a minus here, and I define the left super derivative as 1 plus gamma phi by 2 times d, and the right super derivative as 1 minus gamma phi by 2 times d. So, since gamma 5 anti-commutes with gamma mu, you can see that dl will be nothing but gamma 5 epsilon dou by dou theta L, and when you put 1 plus gamma 5 by 2 into gamma mu, it becomes gamma mu into 1 minus gamma 5 by 2. So, it will become gamma mu theta r into dou by dou x mu. Similarly, if you look at dr, that becomes gamma 5 epsilon dou by dou theta r plus gamma mu theta L dou by dou x mu. So, you can see very easily that if you take the anti-commutator between d say d alpha and d beta, if you take the anti-commutator, then that will be equal to gamma mu epsilon dou by dou x mu. Just as you get the same supersymmetry anti-commutation relations between the fermionic generators, these are called super derivatives. If you look at the super derivative between left and right, dr alpha comma dr beta, that will be equal to 1 plus gamma 5 by 2 or 1 plus gamma 5 into gamma mu epsilon, or you can write this as 1 plus gamma 5 by 2 into gamma mu epsilon in dou by dou x mu alpha beta. Similarly, if you look at dr alpha comma dr beta, if you look at the anti-commutators between the right super derivatives, there will be 1 minus gamma 5 into epsilon gamma mu dr alpha comma dl beta into dou by dou x mu. That is because you are multiplying d by 1 minus gamma 5 by 2 to get this. But if you look at the anti-commutator between dl alpha and dl beta, what is it? You see, if you look at dl, what is dl? dl is gamma 5 into dou by dou theta L plus gamma mu epsilon minus gamma mu epsilon dou by gamma mu theta r theta L or theta r dou by dou x mu. So, if you take the anti-commutator between dl alpha and dl beta, what will you get? You will get an anti-commutator between 2 dou by dou theta L's, which is 0, an anti-commutator between theta 2 theta r's, which is again 0, and an anti-commutator between dou by dou theta L and theta r, which is 0, because they occupy different sectors. Dou by dou theta L occupies only this portion, whereas theta r occupies only this portion, and so their anti-commutators will become 0, which means that dl alpha anti-commutes with dl beta, right. Likewise, if you look at dr alpha and dr beta, this anti-commutator will also be 0. So, only when you take cross commutators, you get a non-zero term here. So, if you want to construct, and of course, they satisfy the property, if you take any left chiral field phi and you operate it on by dr, you will get 0. If you operate likewise a left chiral field, take its conjugate, you get a right chiral field, they give you 0. You can check this by checking the fact that dl or dr acts on x plus mu to give 0, and dr also acts on theta L to give 0, because its derivative with respect to theta r. So, and dr acts on this to give you 0, because by using this property. So, if you take dr acting on any function of x plus and theta L, that will also be 0. That means dr acting on any left chiral field is 0, likewise dl acting on any right chiral field is 0. So, a right chiral field is characterized by the property that the left super derivative dl acting on it is 0, and a left chiral super field is characterized by the property that the right chiral the right super derivative, the right chiral super field is characterized by the property that the left super derivative operator dl acting on it is 0. So, this is a very useful property. This can be used to construct gauge superfields. If I take, for example, dr transpose epsilon dr, since the two anti-commute, see, you have already seen that dr alpha dr beta plus dr beta dr alpha is 0. That means dr alpha dr beta can be written as some operator multiplied by epsilon alpha beta or E alpha beta. Epsilon is a matrix 0 1 minus 1 0. So, in other words, dr alpha I can write dr alpha dr beta, I can write it as dr transpose epsilon dr multiplied by epsilon alpha beta, and likewise for L. So, I have used a special notation for this, I call this as dr square. Likewise, I put dl transpose epsilon dl, I write this as dl square. Now, suppose I take dr transpose epsilon dr multiplied by e power t dot v, then dl multiplied by e power minus t dot v, where v is a gauge superfield brought into the West Zumino gauge. Suppose I call this as WL. Obviously, this is a left chiral field, because if I operate on this by dr, then you are multiplying 3 drs, dr transpose dr, so this is 0. So, dr acting on WL is 0, because when you multiply 3 drs you get 0, right. So, if you look at the transformation property of this quantity, so this is a left chiral field, and if you look at the transformation property under a gauge transformation, what does this go to? This becomes dr transpose epsilon dr, then e power t dot v will go to e power I omega into e power t dot v e power minus I omega star multiplied by dl, then here you are putting an inverse. So, here you will get e power I omega star into e power minus t dot v into e power I omega. Now, you see dl e power I omega star is a right chiral field. So, dl acting on that is 0. So, dl will sail and come here, right, and this will cancel out with this, and since e power I omega is a left chiral field, so e power I omega is also left chiral, so dr will not act on it, it will give you 0. So, this will come outside e power I omega. So, this is the same as e power I omega times dr transpose epsilon dr multiplied by e power t dot v multiplied by dl acting on e power minus t dot v into e power I omega. So, dl will first act on this and e power I omega will come out, then e power minus t dot v will be fixed and dl will act on this. So, if you look at, let us say when dl acts on this e power minus t dot v and e power t dot v will become 0. So, you will get a term like dr transpose epsilon dr multiplied by dl acting on e power I omega. Now, you see you can write this as, so you can write this as, say you have 3 terms dr alpha, dr beta into epsilon alpha beta, and then dl gamma acting on e power I omega. What is this? I can write it as dr alpha into dr beta comma dl gamma, the anti-commutator, minus dl gamma into dr beta acting on e power I omega, but dr acting on e power I omega is 0, because it is a left chiral field. So, this will not contribute. Dr beta with dl gamma is what? Dr beta with dl gamma is something like gamma mu beta gamma into dou mu into 1 plus, of course 1 plus gamma phi by 2, whatever it is proportional to a bosonic derivative dou mu. So, that dou mu will commute with dr alpha, that means I can write it as some a mu dou mu into dr alpha acting on e power I omega. That means this will come out to this side, because it is an ordinary bosonic derivative, and it will become dr alpha acting on e power I omega, which is 0. So, this term will not come out. So, as an effect dl, if you take the term in which dl acts on this, that will not give you any term. So, in effect what happens, okay. So, if you look at this acting on e power t dot v into dl acting on e power minus t dot v under a gauge transformation, generalized gauge transformation, this becomes e power I omega WL e power minus I omega. What is the generalized gauge transformation in which e power t dot v goes to e power I omega e power t dot v e power minus I omega star. So, that e power minus t dot v goes to e power I omega star e power minus t dot v e power minus I omega, and that comes out. So, you can see immediately that WL is a left chiral field, because dr acting on that is 0. There are 3, if you take a cubic dr, that is 0, that is 3 product of 3 drs is 0. So, this becomes a left chiral field. So, you can form WL transpose epsilon WL and look at the F part and look at the F part. This is again a left chiral field because you are not taking conjugates anywhere. So, this gives you a valid Lagrangian which is invariant under supersymmetry transformations, and a quick calculation shows that WL transpose epsilon WL, if I write V in terms of the in the West Zumino gauge, if I write V in the West Zumino gauge, this will be a product of, say, there will be an F mu nu corresponding to the VA component, that is VA mu component, in which you have, which appeared in the superfield in the form theta transpose epsilon gamma mu theta. So, you have this plus you will have a quadratic term C1, say C1 times this plus C2 times a quadratic combination lambda transpose epsilon gamma 5 lambda A plus the auxiliary term C3 into dA square summed over all the A's. So, this will come to be of this form, which is something like the Yang-Mills Lagrangian, the Gaugino Lagrangian and an auxiliary Lagrangian. So, this is the gauge Lagrangian which you can add to it, because the F component of a chiral field, of a chiral superfield is invariant and is a supersymmetric Lagrangian. That means it is under an infinitesimal supersymmetry transformation, it changes by a total derivative. So, if you look at the matter part, matter part is what? Matter part is phi star phi F. Suppose without matter part without any gauge is phi star phi D, and phi was what? Phi was built out of phi x plus theta L transpose epsilon psi L x plus theta L transpose epsilon theta L into f of x. So, if you look at phi star, what is it? Phi star is phi of x plus star plus, which is phi of x minus, you can put a star, phi star of x minus, then theta r transpose epsilon psi r of x minus plus theta r transpose epsilon theta r f star x. So, what is the D component of phi star phi D? This D component will consist of, as we saw, phi into delta phi or phi star delta phi. Okay, it will consist of one term of this form, another term of phi del phi star, which by integration by parts can be reduced to this form. Then you will have in the D term you will have a term coming from the product of these two, that is fx into fx star. So, you will have an f star into f multiplied by the product theta transpose epsilon theta L into theta r transpose epsilon theta r, that will give you a 4th degree term. So, if you take the D part, that 4th degree term will contribute here. Okay, so, it will say something like, say, into constant times this, okay, and then you will have a term coming from the Dirac part. That means, if I take in phi star, if I take the component theta L or theta r transpose epsilon psi r at x multiplied by the cubic part here, which is theta L transpose epsilon dou mu psi L x into theta r transpose epsilon gamma mu theta L, product of this and this, that will give you a 4th degree term, which is nothing but, it can be written as psi r transpose gamma mu, say epsilon gamma mu into dou mu of psi L. So, you get all these terms. Any other term do you get here? You get, of course, from F, from the superpotential part, that is, if I add to this the F part of this, what do I get? I get an F dash of phi into F. So, you get a plus F dash of phi into F plus its complex conjugate. So, if you take this plus F phi, F I get all these terms, and if you ignore the gauge part, then it is only quadratic in F. So, while computing the quantum effective action, namely e power I times the integral of the Lagrangian, and then if you take a path, take any operators and take its path integral, or look at the path integral, say d of all the fields coming into the picture here, d phi star. So, it is, since it is quadratic in f star, the f star part will contribute like in a Gaussian way, that is, it amounts to replacing f star by that point at which the exponential is a stationary function. So, it amounts to replacing, if you take say e power I times some quadratic term f star f plus something like that, then it is equivalent to replacing it by f star f. How do I go behind? Okay. So, you have a term like phi star delta phi plus f dash of phi into f plus f dash of phi star into f star plus psi r transpose epsilon gamma mu dou mu psi l plus phi star phi. So, phi star phi plus f star f, you have these terms. So, it amounts to, it is equivalent to replacing the f by the point at which it is stationary. So, if I say delta by delta f star of this whole thing equal to 0, if I put, I get f dash of phi star plus f equal to 0. That means I replace f dash of phi star by f, and likewise I replace f dash of phi by minus plus f star by f star. So, if I do that, what do I get? If I do not take gauge into account, then I get phi star delta phi plus f dash of phi into f, but f is nothing but f dash of phi star. So, f is nothing but f dash of phi star. So, this becomes mod f phi square. Similarly, for the second term, and f star f will give you f dash phi star, right, it will give you the same thing. So, you will get the constant times f dash of phi whole square plus psi r transpose epsilon gamma mu dou mu psi l, and anything else that you get here, you will get you will get one more term here, because you are looking at, say, you are looking at f star, you are looking at this. So, you are looking at f of phi, the f portion of this, one will, it will be, say, you have f of phi plus theta l transpose epsilon psi l. So, f dash of phi it will be so, you will get a Dirac equation dou mu psi. If you take the field equations corresponding to this, you will get a Dirac equation gamma mu dou mu psi l is 0, and for the scalar field you get delta phi plus a mass term. That means you are having the Lagrangian for the Dirac field. For the scalar field, the Lagrangian becomes simply dou mu phi star dou mu phi plus mod f dash phi square, which is the which is a nonlinear Klein-Gordon Lagrangian. For the Dirac field, what do you get? You get one more term here, right? It will be a kinematic term, which is, okay, if you take the second degree, if you expand this up to second degree, you will get f double dash of phi into theta l transpose epsilon psi l. Now, you evaluate this at x and look at the square of this, you will get a theta l transpose theta l, a quadratic term in theta l coming from here, right. So, you will get another term here, which is nothing but f double dash at phi multiplied by psi l transpose epsilon psi l, that is a mass term. So, if you now look at the field equations for psi l, you will get theta l transpose epsilon psi l and the real part you are taking, right. So, it will be theta l transpose f of phi f, right. So, if you look at the equation satisfied by the Dirac field, psi r transpose epsilon gamma mu dou mu psi l. So, you will get an equation like gamma mu dou mu psi l plus f double dash of phi multiplied by psi l is 0. So, it means that you get a Dirac equation with a mass dependent on the scalar field, right. If you expand this if you expand f of phi plus theta L transpose epsilon psi up to second degree terms in the Taylor expansion, you will get an f double dash of phi multiplied by the square of this, which is theta L transpose epsilon theta L into psi L, into psi L, right, because they anti-commute. Like if you look at say theta L transpose epsilon psi L multiplied by theta L transpose epsilon psi L, you can write it as psi L transpose epsilon psi L, theta L, and you bring that together, right. So, you write it as psi L transpose epsilon theta L into theta L transpose epsilon psi L, and you write theta L as theta L transpose epsilon theta L into epsilon. So, that into psi L transpose epsilon psi L. So, you will get an equation for the Dirac field, you will get an equation for the Dirac field with the mass dependent on the scalar field, which means that by measuring the scalar, of course, the scalar field is a super partner of the Dirac field. Dirac field is a fermionic field, the scalar field is a Klein-Gordon field, which is a bosonic field. So, you get this sort of a situation. So, when there is a gauge present, of course, you can say supersymmetry will be broken, will be unbroken only if the ground state has 0 energy. That you can see from the fact that if you look at the transformation law of delta of psi L, the transformation law of psi L by applying a supersymmetry transformation, it comes out to be proportional to f, right, that is proportional to f. The reason being that f comes with a quadratic term in the theta L, and if you differentiate a quadratic term in theta L with respect to theta L, you get a linear term in theta L which corresponds to this. So, if you look at if you want supersymmetry to be unbroken, then the vacuum expectation value of delta psi L should be 0, which means the vacuum expectation value of f should be 0, right. But what is f? F, as we saw, is f dash of phi in the stationary case. So, if the vacuum expectation of f is to be 0, then f dash of phi should vanish, or equally mod f dash phi square should vanish, which means that the ground state superpotential should be 0. So, supersymmetry is unbroken only if the ground state superpotential evaluates to give you 0, right, only then supersymmetry is unbroken. Of course, you can, what happens in the presence of gauge fields, I shall discuss that next time. In the presence of gauge fields, what happens is that you replace your the matter field by e power minus t dot v, e power t dot v times phi f term or d term like this. So, that gives you an interaction part between the gauge field and the matter field. So, the total Lagrangian is given by this plus the superpotential f real part, and V contain, and of course, a gauge part. This is the interaction between, this is the matter field, this contains the kinetic part of the matter field and its interaction with the gauge field, gauge superfield, and this gives you the superpotential part of the action, plus of course what I discussed earlier, WL transpose epsilon WL F. This gives you the gauge Lagrangian alone. So, in this case you get the, if you expand everything, you get f mu nu A for this plus C2 times lambda A transpose gamma phi epsilon lambda A plus C into dA square, the auxiliary field. This is the gauge Lagrangian. Here you get all those terms which I told you. When you look at e power t dot v phi, that is a bit tricky. You will get an interaction between the matter field and the gauge field part, just as you have an interaction between the Maxwell field, photon field and the Dirac field. You get other terms also here. You get those terms, and apart from that you will get other terms also here. So, the same logic will hold good. Only you will get an extra auxiliary field apart from f, which is dA, which will appear as a quadratic combination. To that you can add a Fayet-Ilopoulos term to this, because the d part of any Lagrangian is invariant. So, I can add a dA here, okay, without affecting the whole, without affecting supersymmetry. That is, the whole action will remain invariant under a supersymmetry transformation. And if you look at this portion, you will get an extra term coming from the d part here, right. So, you will get a d times a dA times e power t dot v will contain a d with a fourth order term multiplied by phi star phi, because that is the part which does not contain any theta. So, it will appear with this. So, you have a dA into f star phi plus dA square, let us say, let us just one component, d into phi star phi plus d square plus a Fayet-Ilopoulos term, which is this, and again this appears as a quadratic combination, linear quadratic combination in the ds. So, you set the value of d equal to the value at which this quadratic form remains stationary, namely phi star phi plus d plus xi is 0. So, you get that D is equal to minus xi minus f star phi. So, for supersymmetry we require that in the ground state, in the ground that is the vacuum expectation values of changes in fermionic parameter, fermionic variables should be 0. If you look at delta of lambda appears in the gauge superfield part, it is the cubic term. So, it will contain a term coming from the quadratic part, right, and the quadratic part in V, this is the cubic part, the quadratic part in V, no, the cubic part will come, the change in the cubic part will come from the 4th degree part. So, that will be proportional to D, right. So, you want the vacuum expectation value of the change in the Gaugino field delta lambda to be 0, which means vacuum expected value of D should be 0, but vacuum expected value of D is simply vacuum expected value of this. That means phi star phi should vanish plus xi should vanish in the ground state. So, you have two conditions for supersymmetry. Namely, if you look at f dash of phi mod square, that should be 0, or equivalently f dash of phi should be 0. So, that then when there are many scalar fields, then you require that dou f by dou phi n that should be 0, and you also require that phi n star phi n, plus xi, okay, that should also vanish in the ground state. So, these are the conditions for unbroken supersymmetry. Now, people asked a question, why don't we observe super partners of particles like gauginos, or why don't we observe super partners of bosonic particles like gravitons, which are gravitinos, in our laboratory? The answer seems to be from the fact that supersymmetry is broken at the energy scales which are seen in the laboratory. That means at a very high energy scale you have supersymmetry, namely at the Planckian scale, where the super partners of particles exist, and due to some mediation, either gravity mediated supersymmetry breaking or gauge mediated supersymmetry breaking, the supersymmetry is broken by the addition of vacuum expected values. For example, if you take messenger superfields and you add those extra terms, then when those messenger superfields acquire, they interact with the gauge superfields in the laboratory energy sector, causing supersymmetry to be broken. That means some of the chiral fields in the higher energy sector, they acquire vacuum expectation value, causing the chiral messenger superfields to contribute to a Lagrangian, which breaks the supersymmetry in the gauge sector and in the laboratory sector, and these gauge superfields in turn break the supersymmetry of the matter. That is what I am saying is that you can look at it from something from this point. Okay, why is it that we do not observe super partners of normal particles in our laboratory? If you take, for example, say you take lambda n, Sn, phi n bar phi n, where phi n bar phi n are matter superfields, and you look at this, Sn is a chiral superfield. Suppose Sn acquires a vacuum expected value. So, it comes here, the scalar part of Sn acquires a matter, suppose it acquires some vacuum expected value, then you have this sort of a thing, right, phi n star phi n or phi n bar phi n. These are the messenger chiral superfields. So, they will cause these are extra contributions to the Lagrangian, which are non supersymmetric, or they break the supersymmetry by when you add these extra terms in, and these messenger superfields, they interact with the gauge particles. How do they interact? Through the interaction phi star e power minus v phi d. So, they will cause a change in the propagator of v, because if you write down the propagator of v corresponding to this Lagrangian, due to this broken supersymmetry it will change, right, or v will acquire there will be a change in the propagator of v, which will create in turn extra terms in the propagator of the chiral fields, in the propagator of the matter fields which you observe in the laboratory. For example, in electroweak unification, where there are quarks, leptons and gauge bosons. So, The idea is that the messenger superfields, they interact both in the higher energy sector near the Planckian scale and in the lower energy sector, causing breaking of supersymmetry in the lower sector by the presence of extra terms in the Lagrangian, which violate supersymmetry. Next time I shall talk about how to write down the superfield equations, how we can write down the field equations in the superfield domain itself. The idea is of course based on a very simple idea that if you look at, for example, k of phi star phi, and you look at the d part of this and you look at d4x, suppose this is the Lagrangian, suppose this is the action for a matter superfields phi. Since phi is a matter superfield, I can write phi as, since phi is a left chiral superfield, I can write it as dr square acting on some superfield S. That is because if you take the product of 3 drs, that is 0. So dr acting on this is 0, which means dr acting on phi is 0. That means phi is a left chiral superfield. So I can replace this by k of dr square into S star into dl square into S, d part, and the d part of this can be written as a Berezin integral d4x d4 theta integral over this. So since S is now an arbitrary superfield, I can carry out the variations with respect to S to set it equal to 0. Likewise, if you have a f of phi f, the f part of this, you can write it as f of dr square acting on S and then the f part and then integral d4x. So if I look at the variation in this, when S is changed slightly, it will give you f dash of dr square S multiplied by dr square delta S, and then you are looking at the f part of this d4x. So if you look at, say, integral f dash of dr square S dr square delta S, and then you are looking at the second part f part of this d4x, I can also write this as integral dr square acting on f dash of dr square S into delta S, this acting on this whole thing into f d4x. The reason is very simple, because if you look at, for example, dr acting on f dash of dr square x, that is going to be 0, because this will contain only terms starting with either constants or terms which contain 2 drs acting on x, and the third dr acting on that is 0. So by integration by parts I can bring this outside, but you see dr, you are looking at the f part of dr square acting on it, that means the second degree part after dr square acts on this. The bosonic part involving space time derivatives, that will give you 0, because that is a total derivative. If you look at the other part, that will give you dou by dou theta r transpose epsilon dou by dou theta r. Okay, only this term will contribute to dr square acting on this. So you differentiate twice with respect to dr, and then you extract the quadratic part in theta l. It is equivalent to extracting theta r transpose theta r, theta l transpose theta l, epsilon theta l multiplied by the d part of this f dash of dr square S into delta S, the d part, because the d part, you see, if you differentiate this with respect to, if you look at the d part of this, it will contain 4th degree terms in theta, which can be written as this, a product of theta r transpose epsilon theta r and theta l transpose epsilon theta r into this. If you take the second derivative with respect to theta r, this will go away and you will get this, and the f part of this will give you this, right. So the f part, if you write down the coefficient of theta power 4 in this, that is the d part of this, and to differentiate this with respect to theta r twice, you will get a quadratic term in theta l. So if you extract out the f part, you will get this, right. So this can also be written as integral f dash of dr square S multiplied by d4x d4 theta into delta S. So if you look at the field equation, if you look at the total variation in the action, k of dl square S star with dr square S d4x d4 theta plus delta of integral f of dr square S d4x d4 theta put this equal to 0, what are the field equations you will get? If you look at the coefficient of delta S star here or delta S alone here, you will get k of dr square S star or dl square S star dr square S, and the derivative of this with respect to dr square S is of course f phi, is of course phi. So, this will give you phi star phi, then delta by delta phi multiplied by dr square S, dr square delta S. You integrate by parts again in the same way, because you are taking d4x d4 theta. So, if you look at dr square acting on anything will give you something smaller than degree 4, or either it will give you a total space time derivative which will vanish, or it will give you something smaller than theta power 4. So, you can equivalently write this as, you can bring the dr square here and write it as this integral d4x d4 theta. You see dr square acting on any function psi will give you something smaller than, either it will give you a bosonic derivative which will integrate out to 0, or it will give you something which has got degree smaller than degree 4 in theta. So, only this term will contribute to this. Likewise, if you look at this, you get integral f dash of phi, and then f dash of phi into dr square of this whole thing, right. So, you had f dash of dr square S into dr square delta S, and then I brought this dr square here, dr square I brought this outside, and then I wrote it in that way. So, f dash phi into delta S d4x d4 theta, so that is 0. So, you get a superfield equations in the form dou by dou delta phi, dou by dou phi of k of phi star phi plus dou f phi by dou phi. So, dou f phi by dou this and then dr square, so that this becomes a left chiral field is equal to 0. This is consistent because if you take another dr acting on this, this is 0, which is consistent with the fact that dr acting on this is 0 because this is a left chiral field. So, this is the way one writes down the superfield equations. You can also likewise define a super propagator and calculate the interaction amplitudes of particles or superfield particles associated with bosons and fermions and their super partners, that is bosonic and fermionic fields and their super partners. You can calculate the interaction amplitudes by drawing superspace Feynman diagrams and using this idea. I think I will stop at this point. Okay, thanks.